I'm back again. If you remember what I was saying earlier, time series are important data type. DTW has been around for about 50 years as the way people use to assess similarity. So I'd like to do a survey to see whether your intuitions correspond to mine. I'd like to ask you of these... Oh, why is that buzzing? Okay. Of these three series, right, so we've got three series that are 5 ones with a -1 inserted into them. So S has the -1 at step 3, T has it at step 4, and U at step 5. Which of T or U is S more similar to? I give you 3 options. It's more similar to S, it's more similar to T, or it's equally similar to both of them. And now I'm asking you to vote. Is it more similar to T? Yeah, T or U. So is it more similar to T?
So S is more similar to T.
Yep. Okay, sorry if I'm confusing. Is it more similar to U? Is it equally similar to both? A couple of votes for that. Okay, is S more similar to itself than it is to T? All right, options. S is more similar to itself, else S is more similar to T than it is to itself, or S is equally similar to T as it is to itself, which I think is going to be Aaron's response. Okay, it's more similar to itself. It's more similar to T. Oh, a couple of people think it's more like T than it is itself. Interesting one. It's equally similar. Oh, quite a few people think it's equally similar to both. Okay, so there's no right answer, of course. So DTW unconstrained says that S is as similar to T as it is to U as it is to itself. Okay, sometimes that might be appropriate because you just have a whole lot of ones and all that matters is whether there's a -1 there or not. So it might be an appropriate answer sometimes. Often it won't be. The dominant intuition is that it should be more similar to T than U. Windowing is the way that DTW controls this over generosity in its similarity assessments. But with windowing, you can only get 2 possibilities. S is as similar to itself as it is to T, and U is less similar than the two of them. Or T and U are just as similar to S as each other, but U is more similar to S is more similar to itself. All right. The more common intuition is that S is more similar to T than it is to U, but it's more similar to itself than to T. And our alternative to DTW, immersed DTW, is able to get this result. Right? It can also get the result that it's equally similar to each other, and can also get the result that it's more similar to itself than to the other two and equally similar to each of them, all depending on the omega parameter, which can be attuned appropriately, just like the window needs to be tuned if you're going to use DTW. Thank you.
So in this poster, we would like to present our recent paper, is the improving position encoding of transformers for multivariate time series classification. As you know, transformers got a huge interest recently, and in the heart of the transformers, we have the self-attention, which needs the position information to deal with the sequential data, and the time series is the very good sequential data. And previous models mainly use the vanilla absolute position encoding and relative position encoding. So we first did an ablation study on the current position encoding. And then we propose two novel absolute and relative encoding. For the absolute encoding, we use the dimension of a model and the length of the series into the frequency terms from which the sine and cosine function was used to produce all those position information. And for the relative position encoding, we use the notion of a scalar rather than the vector to have a more efficient and translation equivalent position encoding. And then we use the strengths of these two proposed position encoding into the framework in which we use the convolution and the transformers at the same time to do a multivariate time series classification. And we conduct the ablation. We conduct the experiment on 32 different data sets. And as you can see on the top right is the output, the critical difference diagram for the different position encoding and our proposed models. And as the final result, you can see that our model, which named ConvTran, is significantly better than the similar convolution and the transformers models. If you like to use the transformers for your time series data sets, I would like to meet you at the poster sessions.
Thank you. Hi, I'm Daniel Schmidt, and this is work that was done by my PhD student, Shu Yu Tu. So the basic problem we're looking at is a fundamental one, estimating sparse vectors of parameters, so coefficients, maybe in a linear model, something else, where a large number of the coefficients may be zero at a population level. And we looked at using something called the horseshoe. The horseshoe is a powerful Bayesian sparsity-inducing prior that has some nice properties in comparison to things like L1 penalization. So L1 penalization, which is common in machine learning, tends to damage non-zero coefficients, biases them heavily when estimating, and the bias increases as the degree of sparsity increases. So in the Bayesian approach, you normally put a prior, in this case the horseshoe prior, which promotes sparsity, put it onto your coefficients and maybe sample, and use something like the posterior mean as your estimate. But ironically, even though the prior it promotes or induces sparsity, the posterior means are almost surely never sparse. So none of the coefficients will be zero. So that's good for prediction, but if you actually want to do variable selection, obviously that's not ideal. So what we did was we used the horseshoe prior in conjunction with the EM algorithm to find the posterior mode. So the posterior mode will be sparse, almost surely. And we overcome some interesting theoretical issues, particularly the fact that the horseshoe prior has no analytic closed form solution. You can't write the prior down. But we used some neat tricks where we reinterpreted the coefficients as the latent or hidden variables in the EM algorithm and used a correspondence between learning hyperparameters and coefficients to end up with a nice fast algorithm with closed form solutions for the updates. And the initial experiments in this paper that was ECML show that it has excellent predictive performance in comparison to things like Lasso, avoids the use of cross-validation, so there's no need to refit multiple times, and generally led to sparser solutions while retaining good predictive performance. So if you're interested in sparsity or any of that stuff, come by and say hello or knock on my office. Thank you. Thanks, Daniel.
Yeah, this is Teresa. This is work done by my PhD student Song Lin and supervised by me and Yuan Fang. So for this work, we look at the taxonomy data. Taxonomy data, the abstract view of taxonomy data is a directional hierarchical graph. Inside the graph, there's only one relation, which is all relation. For example, a cat is an animal, and dogs is an animal. So that's the relation inside the taxonomy data. So why we want to look at the taxonomy data? So because taxonomy is everywhere. So you can, especially when we have larger data, that means, we will have larger and more complex taxonomy data. So for example, the product, the medication, the diagnosis, the law, and all sorts of concepts and the web. So we have a lot of taxonomy data. And the gap is that, So for some existing work in this area, so usually they ignore these two things here. One is the hierarchical semantics among the parent and the child nodes, and another one is the directionality of the is-or relation. So that's why, in this work, we propose a new node representation with the hierarchical information modeled. So basically, for each node, we have two sorts of information there. One is the information carried by the node itself, and another one is the information the node inherited from his ancestors. Then, we got, another contribution is that we have a theoretical guarantee of the directionality of the relationship by applying the non-Gaussian constraint, inspired by the Damos-Gatewich theorem. So the evaluation was done on 2 real-world data set and, comparing with 5 baselines. So if you want to find more, please come to our posters. Thank you.